Today, we dive into a core element of 3GPP's RF framework, power class and transmitter characteristics. These parameters define how strong, clean, and stable a 5G transmitter signal is, directly affecting coverage, coexistence, and device design. In 3GPP specifications, power class defines the maximum output power capability of a user equipment, or UE. Just like LTE, 5G new radio classifies UEs into power categories to match coverage and hardware limits. For example, the most common type, power class 3, specifies a nominal output of 23 dBm for FR1. High-power devices like industrial or fixed wireless terminals may use power class 1, delivering up to 31 dBm. In FR2, where path loss is higher, new classes are introduced, such as power class 1, 34 dBm, and power class 2, 27 dBm for millimeter wave. These categories ensure interoperability and define expected uplink coverage. This slide with more details about power classes, and this slide is intentionally compact. The 3GPP DS documents contain much more details. You can visit 3GPP site if you need to read more details. I'll paste the link in the description for your reference. Transmit power is specified in two main ways: conducted power and EIRP, or effective isotropic radiated power. Conducted power measures what levels the RF connectors, while EIRP considers the antenna gain, the total radiated energy in a specific direction. In FR2, EIRP is the preferred metric, since devices often use phased array with no direct RF port. The 3GPP standard TS38.101 defines test conditions and tolerance limits, typically ±2 dB for conducted and ±4 dB for EIRP, to ensure stable transmit performance. Output power alone isn't enough. Signal quality matters too. Two critical metrics are ACLR, adjacent channel leakage ratio, and EVM, error vector magnitude. ACLR measures how much unwanted power leaks into neighboring channels. EVM quantifies modulation accuracy, a key indicator of transmitter distortion. Typical 5G new radio targets ACLR bigger than 45 dB for most FRM bands, EVM less than 3.5% for 64 QAM. This ensures clean coexistence and reliable demodulation, especially in high-density networks. Another transmitter challenge is PAPR, peak to average power ratio. 5G OFDM signals have high PAPR due to multiple subcarriers, forcing the power amplifier to operate with back-off, reducing efficiency. Modern devices use envelope tracking or digital predistortion to improve linearity without wasting power. These techniques dynamically adjust PA bias or pre-correct signal distortion in real time, improving battery life and thermal performance. Finally, every UE must pass 3GPP-defined RF conformance tests performed under control conditions. Standards such as TS38.101 and TS38.141 specify measurement setups, power limits, and performance metrics. Test case verify EIRP, ACLR, EVM and an output power stability across frequency, temperature, and bandwidth. These validations ensure consistent user experience and prevent interference in real network. Power class and transmitter characteristics form the foundation of reliable 5G uplink performance. They balance signal strength, linearity, and efficiency, the essential trio of RF design. In the next episode, we'll move to the receiver side, exploring sensitivity, blocking, and coexistence performance. Stay tuned and subscribe for more 5G new radio RF features. Thank you.